Hello, after lunch, I think that we can start our very interesting session today, climate hazards and population exposure. We have 6 very interesting presentations from different parts of the world. And I think that all presenters can use 10 minutes for the presentation, maybe 1 minute plus. And then we have enough time, we will have enough time for the discussion. First presenter is Clemens. The floor is yours. Please introduce your team and the topic about high resolution projections of ambient heat for major European cities using different heat metrics. Interesting. Thank you.
Thank you very much. Yes. Okay, so yeah, the title was already said, so welcome very much from my side. Climate projections of the future, they often rely on global climate models. For example, the IPCC Assessment Report 6, many results of this report are based on global climate models. Now, these global climate models, for example, from CMIP 5 or CMIP 6, they have a spatial resolution of about 100 to 200 kilometers. So this is suitable for projections of ambient heat at global or at regional scales. And I'll just show you here an example here for 2 regions from a study of mine. We looked into different heat indicators, and now the orange and red line here are the NOAA heat index and humidex. And you see clearly that in these 2 regions, they have very, very different trends. But what if we want to have projections of ambient heat at small scales, like cities, for example? What do we do then? So there has been a study for Europe. They used these global climate models with a spatial resolution of more than 1 degree to look into climate change in more than 570 European cities. And what they looked up is first here on the left side, it's a change in heat wave days, where you can see that especially in the south of Europe, but also here, for example, in the north along the Baltic Sea, you have a strong increase in these heat wave days. But if you look, for example, in the maximum temperature during the heat wave, then the pattern looks different, and it's especially strong in Central Europe. And then there's another study which used regional climate models with higher resolution. And they looked into the days during which wet bulb globe temperature is above 28 degrees. And here on the right-hand side, you see that for future projections, you see that especially in the south, there are many exceedances of this indicator. So you see that it's like different indicators and also different models, global and regional climate models. And what is now the difference between these global and regional models? So the main idea is that you use the global climate models, the simulations, and you focus on a certain domain, and you use the input of these global models like at the boundaries of this domain. And within the domain, you use another climate model, the regional climate model, to get higher spatial resolution. And you see it, for example, here very clearly for the Alps, that they are much better resolved in the regional climate model projections. And recently, now for Europe, it's called Eurocortex, this regional climate models. So they have reached a resolution of about 12 kilometers, and this allows for assessment at the city level. And I just bring you 2 examples here. Now here on the left, you see London, and you see very clearly that London is much bigger than this 11 times 11, 12 times 12 kilometers. But even for cities like Stockholm, you would on average have like at least 1 grid box that falls within the city limits of Stockholm. So this brings me to the research question. So we know already that ambient heat is projected to increase globally, including in Europe. But the question here is, how is ambient heat projected to change in major European cities based on these high-resolution Eurocortex simulations? And how strongly do these projections depend on the selected heat metrics? Now, as I said, we use these Eurocortex simulations at 0.11 degree resolution. And I just show you now here again, this is like the typical resolution of these models. That for London, for example, you have several grid sense within the city boundaries. And for Oslo, Zagreb, you have at least 1. And we always use the grid box that lies closest to the city center for each of the cities. There are 71 model combinations available from these Eurocortex simulations, which is quite a lot for climate models. And then we use the historical simulations and the RCP 8.5, which is like the really high emission scenario. And to become independent of these high emissions, we evaluate the ambient heat at 3 degrees European warming in Europe. This is relative to 1981 to 2010. And this more or less is this time when global warming reaches also 3 degrees. And then we analyzed 36 European cities, which you can see are located all around Europe. So it's the major European cities. And I used 3 different heat metrics for this analysis. And I will just introduce them now, the results section one by one. So the first metric that I used is the yearly maximum temperature. And this is now the change between 1981 to 2010 and the timing when European warms by 3 degrees Celsius compared to this reference period. And you see quite clearly here that the strongest changes here are somewhere here in Southern Europe. They span like an arc from Spain over Italy towards the Balkan. And you see here these numbers from 1 to 5. They indicate the cities with the strongest increase in ambient heat according to this indicator. The second indicator is the days, or like the number of days per year when 30 degrees Celsius are exceeded at this 3-degree warming. And here you see very clearly it's especially in the south, but almost nothing in the north, which we expect because the south, of course, is also climatologically warmer than the north. And the third indicator is the heat wave magnitude index. And this is an indicator that combines the duration and the intensity of a heat wave into one single indicator. And here you see that again, we have strong increases in the south, but you also see quite substantial increases here in Northern Europe, for example, here, especially in Oslo. And the crucial point here is now, if you compare single cities, for example, as I just said, Oslo, you see that it can be very different, the results, depending on the indicator you choose. So if it's about like for the exceedance of 30 degrees, Oslo almost is like is among the cities with the lowest increase, while it has substantial increase for heat wave magnitude index. And it's even more pronounced here, for example, for Barcelona, which ranks #1 in terms of heat wave magnitude index, but has very few exceedances of 30 degrees Celsius. Now, this is all for daytime conditions, so it's based on daily maximum temperature. And we also performed this using daily minimum temperature, so that's kind of indicative for nighttime conditions. Now, if you check here, like just roughly, you see that the patterns are very similar. But if you look into the change between these two, you see quite some substantial differences. Now here, this is the difference between nighttime and daytime. And I should mention that for the exceedance of nighttime, we use 20 degrees Celsius, which is typically referred to as tropical nights. And you see that generally, you see the increase for these two indicators is less strong during the nighttime. But for some cities, it's different. For example, here for Stockholm, where the maximum nighttime temperatures increase stronger than the daytime temperatures. Or here again, here now for Barcelona or Istanbul, where you have also many more exceedances of nighttime of above 20 degrees. Now, if you look into this heat wave magnitude index, the story is a bit different, because here you see that throughout Europe, nighttime heat waves and heat wave magnitude index increases more strongly than during daytime. And again, you see that especially here in Southern Europe, you have the strongest increases also during nighttime. And what we also did then is that we compared our results to the global climate models, because we wanted to see, are they similar? Is there any change? So what you see here is, again, all the cities we analyzed, and they are now organized like this, that here on the top, you have cities in the north, here you have cities in the south, and then here Eastern and Western Europe. And what you can see here, the Eurocortex, so the regional climate models are in red. So they lie within the range of the global climate models. So they project less extreme increase in this case, the maximum yearly temperature. And it's more or less the same also for the other indicators. So you see that the patterns are very, very different. For example, here for the exceedance of 30 degrees. But you see again that the Eurocortex simulations don't show so many exceedances of these indicators. And it's also similar for the heat wave magnitude index. It's just not visible as well, like as good, because here we use a logarithmic scale because it just increases so much. Now, why might this be the case? Why might ambient heat be lower in the Eurocortex simulations? So first of all, we have different aerosol forcings in Eurocortex and CMIP5 and CMIP6 models. So we heard about this already yesterday, and that this plays an important role because it affects but how much solar radiation is reflected back to space. And for Europe, the global climate models expect that there is a decrease of air pollution. That means a warming in Europe, while the Eurocortex models, they have a constant aerosol forcing. So they don't see this decrease, and so no additional warming from the aerosols. The second thing is an effect that's called plant physiological effect, and this one is missing in Eurocortex models. So if you have plants, they have stomata on their leaves, so it's small openings, and they take up CO2 through them, but they also transpire water through them. And if the CO2 concentration in the atmosphere increases, they are more efficient at taking up CO2, so they close their stomata and also transpire less water. And this means that kind of the net radiation that we have is you have less transpirative cooling, but more warming through sensible heat flux. And this is also, that's what we have in the global model. So this is especially for extreme temperatures, it's important, but it's missing in the Eurocortex models. And then maybe most importantly, that urban areas are only explicitly represented in a few Eurocortex models. So it's, although they have such a high spatial resolution, urban areas have not yet been really the focus of them. And then as the last result, I just wanted to show you here now all the different models that we have. And the main point here is you see that there is a lot of variability. But you see, for example, here one model had RAM3. This has like very strong increases in all of the indicators, while other models have relatively low increase in these heat indicators or in ambient heat. And this means if you do studies with these models, you should use more models, not only just one, because you could just by chance get a model that is very strong, has very strong ambient heat projections or very low projections. Okay, this brings me to the summary. So first of all, the Eurocortex simulations, they provide a valuable tool for climatological assessments at the city level. But there are some caveats because the aerosol forcing is different, the plant physiological effects are missing, and the representation of urban areas is not complete. That means that the interpretation against CMIP simulations to these global climate models remains difficult. And then it changes in the cities, but with distinct patterns. And it seems it's a bit reshuffled here, but it doesn't matter. So first of all, the change in maximum temperature is strongest in the south, and then followed by Eastern Europe. For the threshold exceedance, there's a clear south to north gradient. And for heat wave magnitude, you have the strongest increases again in Southern Europe, but also in Northern Europe, quite substantial increases. And the other important point is that these different metrics, they represent different facets of ambient heat. So depending on what you use them for, you should keep this in mind that your results might be very different for single cities. And I think this is important also for adaptation. And the study is currently in discussion in Natural Hazards and Earth System Sciences. So if you want to have a look, feel free. Thank you very much.
Thank you, Clemens. We will have another next presenter, Gasparini, here. Okay. And you have to switch microphone. And I suggest if there is some emergency question, or we can discuss later on after all presenters. I think that it's better.
Okay. Hi, everybody. My name is Antonio Gasparini. I'm a professor of biostatistics and epidemiology at the London School of Hygiene and Tropical Medicine. I will start with two acknowledgements. First of all, I'm stepping in today replacing the first author, Asia Dimitrova, who submitted this work to be presented here, but couldn't be present. So I'm just presenting her slides. I was part of the team and co-author of the paper, but this comes to the second acknowledgement. My contribution expertise is maybe focuses on some specific areas, much less on other areas. For example, neonatal epidemiology, which is not my strong, let's say, the strongest part of my CV, let's say. So I hope I can provide all the details. If not, I will gently, point you towards, Asia, who can probably be a bit more specific. But I will try my best. Motivation of the studies, I want to highlight two things. First of all, there's plenty of studies, already epidemiological analysis on heat and cold and temperature, let's say non-optimal temperature and mortality in particular. But this study decided to focus on a specific subgroup, which are neonates and newborns, let's say, defined people born within 28 days. In particular, because among other subgroups, these are especially vulnerable to non-optimal temperatures and other stressors. There are physiological reasons, but also logistical reasons, let's say, for these that I will not expand in here. But it was very important to understand what is the impact on these specific subgroups, which is probably very rarely studied if compared to the general population. The other important aspect is to focus on low and middle income countries. Of course, most of the studies and contributed a bit on that, on the health effects of environmental non-optimal temperature. Most of them focuses on high-income countries, let's say. There is already research on that. But in specific, for this specific group, I think it's particularly important because these accounts for 91% of the global burden of neonatal deaths. So it's very important to focus on these specific places. There are other reasons, of course, higher exposure to heat in these places. Mostly they are in hotter places, lower adaptive capacity, and larger population growth, especially in a climate change perspective. So the research objective is to quantify the association between exposure to ambient temperature and the risk of neonatal mortality. The first group, big group defined on these 28 days since birth, but also with a focus on a subgroup, which is the early neonatal mortality, basically 0 days, meaning the same day, the mortality happening the same day of the birth. The idea is to estimate the historical burden and the neonatal death, and also the one attributable to climate change. Again, the focus is not on the future, climate change that we are already experiencing. So, some words on the data. The health data was captured by the Demographic and Health Survey, in particular 2 waves of this survey, the 7th and the 8th, in particular because in here we have the exact day of death for family members. This is a household survey. Of course, we can come back to this later. All of this is reconstructed through interviews, so there is no, let's say, administrative database on this. But of course, we can discuss how this can affect as a limitation the analysis later. But through this survey, it was possible to gather information in a time period between 2001 and 2019 for 29 low and middle income countries. So in total, there were approximately 40,000 neonatal deaths, among which 15,000 were early neonatal deaths in the same day. Now, the good thing of this data is that it was possible to reconstruct with some small error added for confidentiality issues, the residence of all these families, and to link through GPS coordinates to temperature data. And this temperature data is represented by 3 out of the 4 EasyMIP reanalysis models. These 3 cover the period that we were interested in, and through this it was possible to build 2 scenarios, factual scenarios, which are basically the reanalysis series created through this model, but also a counterfactual one, which is a method applied through detrending to reconstruct what would have been, in a way, the the temperature distribution in this period without anthropogenic emissions and, let's say, climate change, let's say. So we have a factual with climate change and counterfactual no climate change scenarios. And for these, both of these, it was possible to reconstruct daily temperatures into community-specific temperature percentiles. So, sorry, I think, yeah. So, going into the method, the idea was to apply, I think there's a slide missing in here. Well, I'll discuss it. It was possible to apply a case crossover approach. I'm not delving into the method. Basically, the idea is to assign controls for each death events based on a fixed strata that are predefined, and therefore they are same weekdays in the months of the day in which the event happened. This, of course, has been already discussed, as several advantages, primarily because you can control automatically for everything that doesn't change in time, especially individual level characteristics, both of the mother, of course, and the child. And through this, it was possible to apply some time series method, basically distributed lag linear models, to estimate the exposure response functions, accounting for up to in 2 days of lag, actually lags from 0 to 2, accounting for, let's say, this lagged effect of temperature, but reconstructed everything in a smooth way through splines, and therefore reconstructing these exposure responses across the whole population. Now, there are limitations here. Given the small sample size, it wasn't possible to do country-specific estimation. So there's an estimation based on percentiles that applies to the whole population. We account for acclimatization because these percentiles can refer to different temperatures in different population. But of course, this represents a limitation because ideally you want each location in a way to estimate the exposure response relationship. Now, these are the results which are representing the exposure response relationships, and we have a point of minimum. Well, these represent, first of all, estimates for under 2 groups of the 3 climate models, well, reanalysis models that we use it, especially because in the factual scenario, 2 of them are identical. It's only the counterfactual changing. And therefore, in the 2 columns, we have these 2, and by rows, we have neonatal mortality and very early neonatal mortality. So these curves represent a point of minimum, which we call the minimum mortality temperature, and in all the cases, they show an increase for heat and cold. Now, the curves are very similar between the different climate models. Probably we expected that, but there are more dissimilarities between neonatal deaths and early neonatal deaths, very early neonatal deaths. In particular, very early neonatal deaths, they show a lower percentiles in terms of temperature and a much higher effect of heat if compared to the neonatal mortality per se. Now, from this curve, it's possible to reconstruct the excess mortality by applying these curves to the actual temperature in the factual scenario. And therefore, we measure that 4.3% of neonatal deaths can be associated to non-optimal temperature, both heat and cold. And these are the mortality rate in all the countries. In here, we show the heat and cold neonatal mortality rate, meaning the excess, let's say, due to heat and cold in blue and red, also separated by extreme and non-extreme heat and cold temperature, showing that there is a huge difference in the impact across places. And of course, this depends on the underlying temperature and the distribution of temperature across places. Again, the shape of the exposure response is the same for all the places, unfortunately. But also it was possible to compare the excess in the factual scenarios versus as a difference in the counterfactual scenarios, and therefore to estimate how much is the proportion of, well, the change, let's say, due to a climate change that we have already experienced. And this is reported in here. And in total, we measured that we have, among these 4.3%, there is a part on heat and cold, and we measured that there will be 175,000 neonatal deaths from heat attributed to climate change, which is a 46% increase if compared to the counterfactual scenario. no climate change, while there is a much bigger difference in cold, just a 30%, much bigger in total for the cold effect. So a much bigger decrease in cold effects. Now, this is the geographical distribution of the effects, which in particular for heat, some places just like Haiti and the Philippines, and some places in some countries in Africa, much more affected than others. And for example, India, much less. And these are the same results instead for the very early neonatal deaths. The main difference in here is the much bigger importance of heat. And in fact, there is a decrease in heat, increase in heat-related deaths, which surpasses in a way the decrease in cold-related mortality in this case. So some conclusions here, both high and low ambient temperatures poses risk for neonatal mortality in lower middle-income countries. We know that there are these are important impacts in terms of numbers and percentages. And although we already know some of the causal pathways, it's clear from this study with empirical data that especially that it affects much more the very early part of life in a very early neonates if compared to others. These are important issues related to climate change, because we know that there will be changes in the future, and therefore there are policy implications in a way suggesting that you need to implement some interventions in order to reduce both the exposure and possibly the dealing with these extreme situations in the future. Thank you very much. Stop here, and I don't know if there is time for questions.
Thank you very much. We can go to the next speaker, Philip. Philip is coming from Austria, Australia, and Germany, and he will explain all other details. We can go.
All right, thanks very much. Good afternoon. Today I would like to present a study on projected heat waves in the context of recent heat extremes. My name is Philip Aglas-Leitner. I'm from the research group of Sarah Perkins-Kirkpatrick, University of New South Wales. And this research is being conducted in collaboration with my two supervisors, Sarah Perkins-Kirkpatrick and Dorothy Stone. Before we continue, I would like to thank the conveners very much for organizing this great session. We live in a time where we are routinely confronted with extreme heat events and record-shattering heat waves. This inevitably brings up the question about what the future might bring and how we can adapt to these future extreme events. And the probably more unnerving underlying question, can we even successfully adapt to these types of events? So we set out on the scientific journey to get closer to answering these types of questions. As adaptation approaches often use past extreme events as kind of a baseline, the overarching research question of this study is, how do future projections of individual heat waves compare to recent heat extremes? To this end, we selected 14 relatively recent heat waves in 14 different regions across the globe that happened between 2010 and 2021. Here you can see a very rough sketch of our 14 regions of interest. I would like to mention that even though we tried, some geographical overlap was sometimes unavoidable due to the dynamic nature of heat waves. We selected our 14 heat waves mainly based on 3 parameters. The first one is that they had to occur during the warmest 6 months of the respective region's yearly cycle. So we're talking about basically summer events, more or less, extended summer events. The second was data availability. And finally, we primarily looked at record-breaking and/or high-impact events. The rationale being that anchoring future heatwave projections to record-breaking and/or high-impact events in the lived experience is essential for effective adaptation, mitigation, and successful communication of how devastating heatwaves might become in the future. Assuming that we have a very interdisciplinary audience here today, I do not want to bother you with too many technicalities, although some will be useful in order to understand the context, so please bear with me. One of those technicalities is our heatwave definition. I'm going to give you a brief overview. We use a minimum event length of 3 consecutive days in accordance with what is often used as minimum heatwave length in the literature, where the regionally average daily maximum temperature is above the day of year 90th percentile for the respective region. Now, our climatological base period was chosen to be in 1961 to 1990. For the climate researchers in the audience, this might be a bit interesting. We used 2 sets of model ensembles. The first one is multi-model ensembles from CMIP 5 and CMIP 6, respectively. And the second one is a set of multi-model ensembles, the large initial conditions of CMIP 6 models. However, for the purpose of this presentation, only the CMIP 6 one, the multi-model one, is relevant. And now, before I continue, before we get to the results section, I would like to give you a brief introduction to our heatwave analysis framework, so it will be easier for you to interpret the results. Our analysis framework basically is based on 4 parameters and additional subparameters where applicable. The first one is heatwave duration in days. The second one is heatwave severity, which is an intensity index enabling interpreting excess heat relative to the regional climatology. The third one is cumulative heat in degrees Celsius. And the fourth one is the percentage of locally affected area, which is an area-based parameter providing information on the exceedance of local, in other words, grid cell level climatology thresholds. This framework greatly increases the ability of individual-based and regional intercomparison, and also provides vital human impact-oriented information by combining both the regional as well as the local scale analysis. So now I would like to show you some of our results. Here in this figure, you can see our parameter correlation analysis for our 14 regions. As this figure contains a lot of information, I admit I will walk you through it. Each individual dot in the subplot represents a heat wave found in the CMIP 6 multi-model ensemble from 2020 to 2100. On the y-axis, you can see the heat wave length in days, whereas the x-axis shows the percentage of locally affected area in percent of the respective region's overall area. In this particular case, it shows the median area. The dot size represents the cumulative heat in degrees Celsius, and the color intensity indicates the severity, which you can see on the color bar on the right over here. The observed reference events that I mentioned before are indicated by the tiny axis over here at the end of the area with a zoom-in window at the other end. And we also, I'm sorry, that wasn't intended. Okay, yeah. We also introduced additional axes to see the distribution of the individual heat waves for the respective axis parameter. In this particular case, you can see the results for SSP1 2.6. For those who are not familiar with climate model lingo, this is basically the second most ambitious mitigation scenario in the CMIP 6 ensemble set. And as far as I remember, if I'm not completely mistaken, at the moment pretty much our best chance of actually reaching the Paris Agreement goal of 1.5 degrees Celsius. You can see even in the case of very ambitious mitigation, we can see heat waves that are still substantially longer and even bigger than compared to our already extreme reference events. As we're currently in Sweden, I thought let's have a closer look at Europe. Here we can expect heat waves that are substantially longer than the 2018 reference event. At the end of the era. Some, especially towards the end of the century, might come very close to even hit our theoretical 6 months limit. In addition, we see that even in this scenario, heat waves are becoming significantly more severe, both of which feed into the increase in cumulative heat indicated by a dot size. And in terms of the affected area in Europe, we can see that heat waves that are substantially bigger by a factor of 1.5 or even close to 2. How much time do I have? Okay. Then I would like to, as a comparison, I would like to show you the same type of figure for a model scenario, which is close to our emissions scenario, to the emissions pathway that we are currently on. In climate model lingo, it's SSP 7.0. And now as a comparison, you can see that as expected, it shows a substantially different picture with a lot more severe and bigger heat waves. When we again take a closer look at Europe, it shows a significant increase in the number and proportion of heat waves approaching our 6 months limit. And even in the case of the median affected area, we can see that heat waves reaching values of above 80 or even close to 90% of the entire continent. So in other words, in those cases, the heat wave will, on average, nearly affect the entire continent. And so I emphasized on average because when we look at the maximum values, at the respective maximum values, we can see that there's a very in the case of Europe, there's a very strong clustering in the right top right corner. These are the values that are reached for at least 1 day during the heat wave. So in other words, for those, at least 1 day during the heat wave is affected by, affects the entire continent as a whole. And for the sake of time, I'm going to skip that to make you keen on reading the final paper and skip right to the summary. We can see that recent extreme heat waves are basically being dwarfed by their projected 21st century counterparts. Without even moderate reduction in greenhouse gases, the reoccurrence probability and exceedance of recent extreme reference value is significantly increasing. And on top of that, the exceedance is still plausible under aggressive emission reduction scenarios. So we argue that ambitious mitigation is, of course, urgently needed to be able to adapt at all. However, it is also necessary to consider heat waves well outside the lived experience for effective adaptation measures. Thank you very much for your attention.
Thank you, Philip. Our next presenter is Håkim. I would like just to underline that we have almost 50 attendees online, and we expect the questions from them, and that we have a lot of people who are interested for our session. Thank you.
Thank you. This is my title, which is just a part of today's talk. Today, I'm Håkim from the Graduate School of Public Health, Seoul National University, South Korea. And today I'd like to present more, bigger project than this small specific problem. So I will introduce the big project called Motive, and this is a very big project. We have several sectors, including health. So we made a user interface called Motive Health. So I will talk about this. And then the heat wave is just one component of this Motive Health. And then some discussions. So the Motive is for model of integrated impact and vulnerability evaluation of climate change. This is a big project funded by Korean Ministry of Environment, and 7-year project which has just ended 2021, and second stage is going on now. So in this project, we aim to develop a model, including a user interface for combining several sectors like health, water, agriculture, forest, etc. So in this project, within sector, we'd like to have some connections between components, and then we'd like to have a link between sectors. For example, health, we want to use some information from water, agriculture, for example, which is very challenging actually. So that's something we'd like to do. So each sector developed their own models, and then try to think about how to change the information between sectors. And we have version 1 for developing after the 7 years, and then we are still updating the project. And let's go into the health sector. The health motive has 6 components: heat wave, ozone, PM10, and 3 infectious diseases such as malaria, chuchugamushi, and waterborne diseases like those information came from the National Health Insurance data. We have one system covering all the people, so it comes from that. And then we have 230 the local governments. So our population size of Korea is like 50 million. So on average, the population size is 200K per each region. But there are big heterogeneity in terms of population size. Smallest is 10K and largest is like 1 million. So huge difference in terms of population size for the analysis unit. And then this 20 years of data is a baseline period. And then we basically applied 2-stage DLNM model, typical time series analysis. And this is the, sorry for Korean characters, but this is the user interface for our health motive system. So we have 6 components: ozone, PM10, heat, malaria, chuchugamushi, and waterborne disease. And then those are the 230 small area. This is showing the mortality due to heat. And this is the metropolitan area of Seoul, and second largest area over there, Busan, we call it. And then show the regional distribution. Those are the big cities, and then those are the rural areas, actually. And 5 levels of heat wave risk over there. And then at that time, we just simply use RCP scenarios. And then in addition to 6 components, we put so-called comprehensive health impact evaluation. This is just for one specific location, comparing 2 locations in the urban area, showing a heat wave, ozone, PM10, malaria, chuchugamushi, and in fact, the chuchugamushi and waterborne diseases, comparing 2 regions. Because this is urban area, they have high risk of heat wave, ozone, and PM10, much less risk from the infectious diseases. and these are the ranks out of 230 local governments. So the local people will immediately know that they have a higher risk for air pollution and heat wave, and relatively smaller risk for the infectious disease. So we provide this kind of diagram for all 230 local governments so that they can be prepared for the major risks of climate change related problems. And currently we are using SSP scenarios. And then one of the problem is that the question we got from the field is that they have several policies. So they are very curious about the effectiveness of the policy. So if we do this, then the future impact, what is the future effect? Will be effective or not? So that means that we have to include those kinds of components into our model, which is very challenging. So the implementation of policy effect is one of the challenges we are dealing with now. And then the other problem is that, as you can see, this kind of non-parametric shape is hard to handle for the local people, actually. So we are thinking about applying some simpler method, like we call it a linear, piecewise linear model for the impact of high temperature and low temperature and zero in between. So those kind of a simpler model for the temperature mortality relationship is another thing we are considering now. So this is just an example of local dose response curve for using simpler models. And then to produce this, we at the second stage, we put local variables into our model, including the policy indicator variables of the policies, because each local government are using separate and different policies. So which policy is the best? That is their question. And then heat wave components. So this is very typical for the time series analysis, but we put local variables, including policy variable, at the second stage meta-analysis procedures. So after running this second model, as you can see, the local, all the dose response curves are somewhat different depending on the location after adjusting the effect of policies. So these are some examples of the specific regions. So in this case, you see high temperature effect over there and a little bit slow effect over there. Interesting, this is most southern hottest place, but they're well adjusted for high temperature. This is northern part, but they are less prepared, I think, in this case. And this is the plot for the whole nation. So there is a national representative curve, dose response curve. And the definition of heat wave and cold spell is defined by this, but this temperature itself has some distribution like that. And this is the result depending on the scenarios we are currently doing, that the death number will be increasing after years, and then you can see the components of the adaptation or scenarios over there. And similarly, that is the death rate per 100,000. The patterns will be very similar. But interestingly, over here and there, the SSP1, the future is much better compared to other SSP2 and 5 in this case. Similar pattern over the death rate over here. And this is actual number and the relative rate. As you can see, actual number is much higher in the metropolitan area. But if you see the relative rate, this is opposite. The rural area is much higher rate, which can be understandable. but within for the communication, this is has very different approaches. So which number is more important, especially for the local? It's not easy question to answer, I think. So we developed a tool, and this is kind of somewhat technical, but small error problem is we are facing. And then integrated assessment, how to combine water into health or agriculture into health, is still we are doing. And I think two-stage meta-analysis is one of the approach we are taking. And then evaluation of the policy is another challenge we are facing. And I'll skip this. This is it. Thank you.
Thank you. Ivan is our next presenter. I think that he will bring us one foresight story. Okay.
Perfect. Yeah, this works.
Thank you. The floor is yours.
Good. Hi, everyone. I'm Evan. I am postdoctoral researcher on climate change and health impacts at the University of Bern, working for the Erskine Center for Climate Change Research and the Institute of Social and Preventive Medicine. And our group looks at a variety of exposure. So we look at droughts, urban heat islands, and the impact on human health. But today I will present you a study on the nationwide projections of heat and cold-related mortality impacts under various climate change and population development scenarios in Switzerland. We primarily look at the role of population aging in there. So we know that globally about 5 million deaths can be attributed to non-optimal temperature, of which of all heat-related mortality, 37% can already directly be attributed to climate change. So that's a substantial amount worldwide. However, when we were zooming into Switzerland, we can see that 180 deaths occur annually related to heat in the period between 2009 and 2017. However, as we all know, like the year 2022 was a very hot year in Switzerland. And as a result, we also saw a huge uptick in the impacts. And as a result, more than 600 deaths we estimated could be attributed to heat. However, of those 600 deaths, more than 60% could directly be attributable to climate change already. So this gave us a small omen to the future, like what the future would look like. And however, the future impacts really depend on a couple of factors, right? So we have mitigation. Depending on mitigation, the effects can change. Depends on adaptation, but also on population vulnerability. Because previous studies, as you can see on the right-hand side, have shown that the risk is much higher for heat and cold in the elderly population. So the older you are, the larger the risk for the effect of temperature. And this should also be considered in future impact modeling. So when we have a higher older population, we expect that the population is more vulnerable and thus the impact should be larger. Now, in a retrospective study in Switzerland, we've done this sort of analysis in a previous paper, and we found that over the past 50 years, 50% of the increase in heat-related mortality could actually be attributed to the increase in population vulnerability and population aging. So if we have done this in the past, and we can see in the past that this is such a huge contributor, what would this look like in the future then? So here we aim to model the heat and cold-related mortality impacts for various climate change scenarios and SSPs, and to estimate the individual contribution of population development and the temperature towards the overall mortality. So when we think of mortality impacts, of course, we think of the classic climate framework, where we look into temperature. So we use different RCPs, and we combine this with population data. And we use also various population data, various scenarios. So we use mortality under SSP2, under SSP5, and this changes for, so the demographic structure changes. Then we also use different vulnerability functions. So we use functions for under 75 and over 75, and that has to do a little bit more with power. So what sort of data did we use? Well, first, to kind of get an exposure response function, we used observed temperature data in Switzerland between 1990 and 2010 on 2 by 2 kilometer high resolution grids from reanalysis data provided by Meteo Swiss. Then we linked this to mortality data, which were over 1 million death records in this specific period, and was divided in Switzerland in 143 districts. And based on the observed temperature and mortality, we created those exposure response functions, and then we started to use the modeled data. And we used the modeled temperature data for RCP 4.5 SSP2 and RCP 8.5 SSP5 from the CMAP5 data. And we use CMAP5 data, and that is because although we know, of course, that CMAP6 data is available, if you look at Switzerland, it's highly heterogeneous, a lot of mountains, so we prefer to have the high resolution 2 by 2 kilometer projections rather than the new CMAP6 data to show our point. Then we also use population projections, mortality rate projections, and based on the population and mortality rate, we reconstructed or projected basically the daily all-cause mortality in the future for different scenarios. So I'm not going too much into the discussion of the methods because Antonio himself already explained some of it. However, in the first stage, we created an exposure response function for the under 75 and over 75 for every district in Switzerland using Diehl-Nems and Classic-Poisson time series regression. We conducted the second stage meta-regression to pool the estimates, gain some power, and re-predict. And finally, in the third stage, that is kind of where everything comes together, where we use the exposure response function. We apply different temperature distributions depending on the RCP scenario, and we also use different population scenarios, vulnerability, and based on that, we estimate the attributable number, attributable fractures, and the rate related to heat. And we report it by warming target. So we report it by 1.5 degrees Celsius, 2 degrees Celsius, and 3 degrees Celsius. So when we look a bit at the RCP 4.5 and RCP 8.5, here in the lines, we basically see that the mortality is decreasing in under 75 and indicated in green. Indicated in black or purple, we see the mortality for the over 75, and in pink, the all-cause mortality amongst entire Switzerland. Then something else we also see is the difference in warming target between the two scenarios. So RCP 4.5, of course, reaches 1.5 and 2 degrees Celsius for a specific period, and RCP 8.5 also reaches 3 degrees of warming. Now, what is most interesting is actually that in RCP 4.5, we have a much small, substantially smaller population compared to RCP 8.5. However, the mortality rate in RCP 4.5 is going to be much larger than in RCP 8.5. And then as a result, our yearly all-cause mortality will be higher in this scenario, which is important to explain the next findings. So when we look at these findings, we see a substantial increase in cold-related mortality from 4,000 deaths today per year, compared to almost 6,500 deaths under 2 degrees Celsius in RCP 4.5. If you look at RCP 8.5, we said that under 2 degrees of warming, this is not 6,500, but this is 5,000. So it's substantially lower. However, when we look at the heat-related mortality, we actually see a very similar trend. And that is that in the baseline, we have about 300 deaths per year. And in RCP 4.5 and the 2 degrees Celsius, we will have 1,200 deaths. So that's a fourfold increase. If we look at RCP 8.5 on the 2 degrees of warming, we see only 800 deaths. So that's not so it's a bit more than a twofold increase. So it's a substantial difference. Although at the end, at 3 degrees of warming, what is reached by RCP 8.5, we end up with a substantially larger number of deaths compared to RCP 4.5. So it's a bit striking that under RCP 4.5, under the same warming levels, we have a much larger cold and heat-related impacts. And then the question, of course, is how do we explain this? Well, here we can see the contribution of population and climate. And in RCP 4.5 for cold-related mortality, we see, of course, the same decrease in, so basically in yellow, what we see is the decrease you would expect if you just shift the temperature distribution over the exposure response function, and you would see a decrease. However, in green, we see the contribution of population aging and development over time for cold. So you can see that in the scenario of 2 degrees, we have a substantially larger contribution of population, increasing the attributable number to cold, which is much higher than compared to RCP 8.5. So we also see a very similar pattern for heat. Now the only difference is that under 2 degrees of warming in RCP 4.5, the population aging is already a larger driver, whereas in RCP 8.5 and the 2 degrees of warming, temperature would still be a main driver. So that is the main result for heat, and we can say that there's a large net increase also in heat and in cold. So when we move a little bit away from just also like population development, there's another aspect that should be considered, and that is currently in progress, and that is that we also look into urbanization. Because we know that urban areas tend to be much more vulnerable compared to rural areas, and this is particularly in Switzerland, these results. And when we start to project in the future in the various SSP scenarios, we know that today some regions are rural, but they are going to be much more urban. So we also would like to project use the same sort of analysis to implement a shift from rural to more urban populations. And that's currently something we're also incorporating in this stage as well. So very briefly, heat-related mortality is very likely to increase sixfold under the 3 degrees of warming in Switzerland. The contribution of this increase can, for 50%, be attributed to climate change, and the other 50% is most likely to be driven by population aging and development. And this basically means that population development exacerbates the heat-related mortality in the future. When we look at cold-related mortality, surprisingly, it will also increase despite climate change. And this is, of course, also because of population development. So basically what happens is that population development counteracts the benefit that we would expect with a reduced number of cold days. So and there are a couple of challenges, of course, or like limitations we should be aware of. And that's a bit of the causality of cold-related mortality because it's not as straightforward. And there are many uncertainties besides mitigation and urbanization and population development. And one of those uncertainties is, of course, adaptation, because we would assume some sort of adaptation over time. However, this has not been included in this study, and in most studies that does not occur because it can be sometimes quite trivial to include some sort of assumptions on adaptation. So much more work, of course, is required on that part. And yeah, if you want to find the study, it's already published in Environmental Research Letters. You can scan it there, and I'm happy to take more questions at the end.
Thank you, Ivan. We have one more presentation. Do you have presenter? Temperature modifies the association between air pollution and respiratory disease hospitalization in an industrial area of South Africa. Jenny. Okay. Thank you. The floor is yours.
Here.
Yes.
Great. Hi, everybody. I'm going to present this talk on behalf of my co-authors, Nandi Mwazi and Bukula Olotolo. So the talk is on temperature modifies the association between air pollution and respiratory hospital admissions in an industrial area in South Africa. So the study results were published in the Clean Air Journal. So if you want to go and download it, you can find more information on it. So most of you probably know about the WHO Air Quality Guideline Report that came out last year, September, the most updated, basically research of thousands of epidemiology and toxicology studies that summarize the evidence. And that's the reason why the WHO guidelines were actually reduced. So although air pollution in some parts of the world came down, in other parts, like especially low middle income countries, air pollution is actually going up because of urbanization. But although air pollution levels came down, the mortality rate did also not came down. So people are still dying, and literally just by breathing, 7 million people are dying every year due to air pollution. And now the burden of disease linked to air pollution is similar to unhealthy lifestyles or even people smoking tobacco. And it's recognized as the biggest environmental threat to human health. And air pollution literally affects everybody, even in Stockholm, where it looks pretty clean. If you're going to walk around with a low-cost sensor, I'm sure you're going to pick up air pollution. So in South Africa, it is projected that temperature will increase 3 to 4 degrees around the coastal areas, and it will actually increase more inland. 6 to 7% degrees in the next 80 or so years. And this is just a picture of the current Köppen-Geiger climatic map of Africa. And it will be interesting to see what this map will look like in a couple of years at the end of the century, how the climatic zones will shift. Perhaps the entire South Africa will be red, will be an arid region. But it's also projected that the eastern parts, where Johannesburg and Pretoria, the large cities are based, will actually experience more rain, so it will become wetter. And it may also lead to more infectious diseases or malaria, whereas the western part, where Cape Town is located, at the bottom, will actually become drier. And why we did this study, globally, fewer studies looked at this temperature effect modification on hospital admissions. Most studies look globally at mortality. So there's actually a research gap in all the countries to do studies using hospital admissions and not just mortality. And of course, in Africa, few studies looked at this at all. So the aim, as I said, was to look at how temperature may modify the effect of air pollution also on hospital admissions in an industrial area called the Vaal Triangle Air Pollution Priority Area in the country. And that was done during a nearly 7-year period. We only used hospital admissions up to February 2020, because in March 2020, the first case of COVID came along, and we did not want to mix the effect you may have with the rise in respiratory disease hospital admissions. So most people find this fascinating. If you look at the world map of where there are air quality acts, you will actually see in Africa, it's only a few countries that do have an air quality act. So the government has a legislation obligation to mitigate air pollution exposures and to bring it down, where in the rest of Africa, literally, they can just pollute as much as they want to. And this is coming from a report by the United Nations, and the latest report I could get was published in 2020. Why I'm telling you about the Air Quality Acts, in South Africa, according to our Air Quality Act, 3 air pollution priority areas were declared. It's this area we are talking about now, the Vaal Triangle Air Pollution Priority Area. It spans 2 provinces, and that also makes it difficult to control or to mitigate and to bring down the levels, because on the provincial level, the act is also spread across 2 different provinces. So provinces may say, your part is not in my province, my part is not in your province, so it's not my obligation to bring down the air pollution levels. So on a legal basis, it makes it very difficult. Then there's 2 other more air pollution priority areas. So we obtained hospital admission data from 2 private hospitals. Currently, there's no publicly run government hospital that has electronic data. So it makes it very difficult to do these kind of research where you don't have public hospital admission data in electronic format. So keep in mind, only 16% of the population, so it's literally upper classes, who can afford a private medical aid to go to private hospitals. So the results we see here, you cannot really extrapolate to the rest of the population. You can literally just extrapolate it to the higher socioeconomic status groups. And then we obtained pollution data, PM10, PM2.5, black carbon, NO2, SO2, and also ozone from 6 monitoring stations. And those are the ones in black. The ones in red and in green, we also actually wanted to use. That's operated by the city of Johannesburg. But the data quality was so poor, we could not use the data. So eventually we just used the data from the monitoring stations indicated in black. So we ran a case crossover epidemiology study. We focused on the shorter lags, lag 0 to 1. That's what most studies did, and we want to compare our results to what other studies did. And we adjusted for public holidays and apparent temperature. And how we investigated the modifying effect of temperatures, we used look at low, moderate, and high temperature days. And we used the percentiles to cut the days up, like done in other studies. And we also investigated susceptibility by age and sex, and of course, we obtained ethical approval. So the results. So here you can see when we look at just a time series plot of respiratory hospital admissions, clearly it's like what you see all over the world. The hospital admissions normally go up in wintertime and then they drop in summertime. And most of the deaths were, or half were from males and also young children. And you can now actually see why the area was declared the air pollution priority area. Because more than 50% of the nearly 2,600 days were above the WHO daily guideline values. So it's a highly, highly polluted area. For instance, if you can see over here, the PM10 level, the highest was 132 micrograms per cubic meter. So that's what, nearly 4 or 5 times the WHO guideline value on 50% of the days. So that's quite hectic. And then the South African government also have a air quality standard, but those are more lenient. And for instance, the PM 2.5 levels were only exceeding that on 70% of the days. So these are all the results we have. Literally, we cut and paste from our published article. So it's a lot to look at. Just briefly, when we ran the analysis over the entire temperature range, we did not pick up any significant findings really for PM10, PM 2.5, and black carbon. But in general, we found those increased the respiratory disease hospital admissions. For NO2 and SO2 and ozone, we did find significant findings when we looked at the entire range. And then when you start looking at the low, moderate, and high temperature days, one could see on moderate days, the association was actually much stronger compared to the other days, especially for PM10, PM 2.5, and black carbon. And it's quite interesting, a lot of studies, even globally, they did not look at black carbon and how those effects may be modified by temperature. So black carbon had a stronger effect than PM 2.5, and PM 2.5 had a stronger effect than PM10. So that's actually quite nice to see. The smaller particles can cause more damage because they penetrate much deeper into your lungs. So it was quite nice to see that. But it was also interesting to see that the gaseous pollutants, NO2 and SO2, had stronger effects. But of course, this is only one study that's done. One must go and have a look globally. Did other studies also see stronger effects for NO2 and SO2, and what were the possible explanations for those? So in conclusion, we did see a modifying effect of temperature, and we mostly saw on moderate days a stronger effect of the air pollutants compared to low and high temperature days. And in general, the elderly and also women were more at risk. But of course, like I said, more studies are needed. Thank you.
Thank you. Now we can open floor for discussion and for your question here and online. Hans will help us. I have one question for all presenters. Last presentation mentioned the quality of data. For me, it's a question. You are using a lot of data, different data. Are you satisfied with the quality of data? And do you have any obstacles during the process of bringing data for research? That is my question for all of you. Okay.
Related to the study I showed, the quality of data, of course, is not the best, but there are issues about accessing and actually gathering the existent itself of the data. In this case, we used reconstructed data through interviews, which is not exactly the best you can do, but of course, there's pretty much nothing else available. There's always a trade-off between the quality of the data you can get and the availability. And I think, especially in low and middle income countries, this becomes, very important. So in the future, I guess we are addressing this issue, for example, in terms of exposure data with reanalysis data that I presented, but in terms of the health data, we'll be stuck with that for a long time. So I think it will be better to have in mind that better data needs to be gathered, and especially systems of data collection needs to be implemented.
Thank you.
Maybe also from the climate modeling perspective, that's what I showed, that if you use different models, they also have different assumptions. And I think this is a key challenge because, we have the global, like IPCC and so, they have these global climate models, but the climate services, they want to know locally what is happening in their countries. So they use a lot of regional climate models, and so far they're not really totally aligned. So you could just have difference just out of this. And it's not because we don't have the data, it's just because they are not using all the same scenarios. But for those, I think it will get better. But of course, like in modeling, you always have improvements, and like in the reanalysis data sets you also use, there is this area 5 lands is maybe the highest spatial resolution, but they also do not include urban areas. So if you really want to look into those, I think it's good if they will include in the future. But I think I'm confident that more people working on it, higher spatial resolution. That's at least what history showed us. People then also improve the models. But currently, there's also some inconsistency there.
I have a difficulty, especially for the social science data, including population size and mortality for the future. Especially in the East Asian context, our fertility rate is so low. South Korea is like 1.8 or something. So we are diminishing. And Japan and China is facing similar problem, 1.2 or 3.4. So it is very hard to predict the future situation of our population, and the age structure will be definitely changing a lot, which has a huge impact. I think that has a more impact than climate itself. So that's one of the difficulty I'm facing.
I could quickly share some of my thoughts. Like I already pointed out the example of our climate data that we're using for the projections, like whether you use CMAP6, low resolution, globally available, or like downscale 2 by 2 kilometer CMAP5 data. So it's always a bit of a question, like what is your question in epidemiology, and what sort of exposure data does help better with answering your question? So I think that is one of the main, considerations you have to make when we do a study. On the other side, as you can see, of course, we've used mortality because it's a very often used outcome, because it's, very direct, it's very clear. And we've also been, we are currently trying to work also with other sort of data, for example, hospital admission data, or even like treatment in hospitals. But then it becomes a bit more complex because a GP or a medical doctor in a hospital assigns a specific code, what they think the disease is with the treatment. And usually it's very hard to kind of translate the codes they're using into something that we can use for our analysis outside of using count data. So it can be a bit it's a bit difficult from both sides, whether you look in the medical field or in the climate science field. You always have considerations to make, and it needs to be practical at the same time too. So it's never very straightforward, I would say.
Thank you very much. I'm coming from the population of public health professionals, and we are unsatisfied with the medical data and with our cooperation with governments and with the clinicians. How we think that we should do much more to bring the better quality of data to climate scientists for the results. Okay, thank you.
I don't know if anybody else wants to take up but I had a clarification question to Antonio, and then I bring up my question. And this neonatal data, I know this DHIS survey, and I know that they, as you said, it's reconstructed interview-based data, and I know that they track the 27 days neonatal death, which is why probably you have that indicator here. But how did you track the temperatures? I'm still confused. Maybe I missed that in your slides. Did you have the locations of the participants? Or?
Yes.
Yeah, okay. No, but they can't hear you online.
Well, in terms of the health data, as I say, it's reconstructed. So they gather information both on the day of birth and day of death of the baby. Of course, there can be some errors. As I said, given it's a case crossover study, possibly this will end up in a dilution of the effect, actually. So it's non-differential, let's say. So it's less concerning if compared to others. But in terms of the data, they have the actual location of the families. I think my recollection is that most of the people are not moving as much as in other high-income countries, and therefore they stay in the same location or very, very close to it for all their lifetimes. I'm not sure, and I should ask Asia if they have information about residential history. I don't think so. But in a way, apart from that, it's a very precise location, and they map the temperature data based on that location with a slight error added for confidentiality purposes. But then they link this data with climate reanalysis global data. So those are relatively valid, or let's say relatively precise and available for the whole period without any missing. So that part is really, in a way, sophisticated.
Thank you. Now I ask my question, which is probably for all speakers, and it's a question that Antonio and I have been discussing. What do you do about adaptation? I think a number of you brought it up. And basically, there is this whole theory that adaptation should reduce the impacts in the future when you look at the scenarios, SSPs, RCPs, whatever. But nobody has been able to accurately define how to include adaptation in. So your thoughts on that? All of you who mentioned this point.
Yeah, I can start maybe on this. So yeah, with adaptation, it's very complex because there are a lot of assumptions you can make. You can say, okay, we reduce the risk function by X%, we bring it down. But on what sort of evidence is this based, right? So I think it's first key to understand, let's say, okay, if you increase greenness in a city by 10%, what is then the risk reduction you get? And then you can start model different sort of adaptation strategies into the projections. But what we usually see is a couple of assumptions. So people say, okay, we shift this temperature of minimum mortality, we shift it according, like with the temperature increase, or we just simply reduce the function by 20%. So it's not based on evidence, more on like, yeah, some assumptions. And I think as the community, we should really focus a little bit more on better modeling adaptation factors. And it's being done, but it turns out to be very complex. But we should integrate those sort of adaptation studies into the projection studies. And I think it should be based on empirical data. But that is my view. And if other people have different views, please.
There's something we actually try to do to have somewhat different dose response curve for different regions. So we use, for example, greenness or the percentage of health for the total budget among the total budget. Those are the input variable at the second stage. So if you compare two local governments with different greenness, then the steep, but the dose response curve at the high temperature will be slightly different. And we think that's the effect of greenness, for example. Or the other policies, you can do it, actually.
Well, I have a quick and simple answer that you mention adaptation a lot in grant applications and in Twitter, but you ignore it in your publications, in your analysis. No, well, actually, we try to do some work as well. Most of that follows what Ho have been doing in a way to try to model these kind of interaction through an interaction, or to a second stage, let's say, modeling the change effect modification on different factors. It's extremely difficult, especially because most of them are highly correlated, and therefore, if you look at one of them at a time, you're not sure that you're picking the right driver. And if you look at many of them, it becomes a mess in terms of modeling. So we tried something, but actually, honestly, we found very little signals for single drivers, while a lot of heterogeneity that can be explained by other places. So my point will be that still we don't know what are the most important drivers.
That's a very good point. So we just gave up to put so many variables. So later, we just tried to cluster the local governments within 5 categories and see what are the characteristics of the good government versus to better performed area. Then we can see what is the difference between those areas in terms of policies. So that's what we are trying to do. Just putting everything is just impossible.
Thank you. Hans, do we have any question from? Okay.
Hello, I'm Jonathan Boujon from University of Bern. I'm a climate scientist, and so one of the things I'm looking at is how exposure changes per degree of global warming. And what I see is that when you look at extreme temperature and population-weighted extreme temperature changes per degree of global warming versus extreme moist temperature population-weighted changes, the extreme moist temperature grows exponentially relative to the extreme temperature. But the analysis that we saw here is all on temperature. And what kind of studies or ideas are people coming up with to try to actually tease apart that aspect of climate change that is looming and growing rapidly?
Well, I'll take it from here. Well, we've done a bit, some studies already, especially in the MCC network on these, and there is this tension, I would say, between climatologists and epidemiologists about which one is the right index to use. Honestly, we have started using dry bulb mean temperature because it was the easiest to use. It was the most available. It was also the easiest to communicate the results for, because everybody can understand it and it can be measured anywhere at any time. However, there is this issue that there are physiological evidence that humidity plays a big role in pushing your body, let's say, and increasing, in a way, the potential effects. But we actually found very little evidence of that in many of the studies, especially on mortality, all-cause mortality. There seems to be very little added when we add the humidity to these studies. Of course, all of these are roughly aggregated data at the ecological level, so you can miss some signals, especially. So we don't pretend this is the final answer, but we found ourselves in a position in which we tried different indices, And actually, the best performing most of the times is dry bulb temperature. Instead, another index, just like the WBGT, UCTI, and many others. So this is not the answer, meaning we need to use this index, but probably more research needs to be done in terms of understanding exactly how the physiological evidence translates into the epidemiological, empirical, let's say, results that we see around. So we don't have a final answer.
We have one more question.
It was just a quick add-on comment to that. Coming from Queensland, a tropical area in Australia, we started investigating this. And while it is more damp, more humid in the tropical regions, the type of heat is different. You don't get the sort of really high 45 degrees, but you might get 35 degrees 10 days in a row, or you might get a nighttime temperature. So I think there's some work to be done to unpick that, and the actual humidity might be a confounder, and it might be the different type of heat might be what's actually going to drive it in the tropical regions.
Thank you. Any comments or yes?
No, it is a very thank you for all the presentations. They were magnificent. So for Ho, so you worked and developed this tool, and I just wondering if you had any good experience working with policymakers and how they were included into this co-creation of the tool, or if not, you have some plans.
So we have new administration. All right. So having a good politician is very important. So they cut our budget. So we are having difficulty now. So that's the political power, empowerment is very important. That's what I realized after several years of experiences. And then empowering people, that is also very important. For the local level, the people vote for their leaders. So there it's easier to communicate with people. But at the top level, I mean, central government is very, very difficult. I guess that's what I can say.
Thank you. Thank you, Hans, for co-chairing, and thank you all for active participation. I'm coming from Serbia. My name is Maria. I'm a professor at Medical Faculty, University of Novi Sad, and here I'm a member of advisory board of ENBEL project, and I wish to thank you, all of you, for your active participation. Thank you.